welcome to this webinar about groundwater control for construction. And on behalf of the Swedish Geotechnical Society, I'm very honored to welcome Martin Preene with us today. It's fantastic to be able to have someone from abroad in this easy manner having a talk about this very interesting subject. But I'll leave it to Lynn to make a short introduction of Martin.
Martin Preene is a very experienced, what could we say, dewatering hydrogeologist, or the words are always difficult, what we name different things, but very experienced in dewatering of excavations and construction sites. And I think you might be familiar with the book Groundwater Lowering in Construction, which is actually, I call it my groundwater Bible. I love that book. And Martin will give us a presentation that provides background to commonly used methods for groundwater control and dewatering, such as pumping techniques and exclusion methods. And yeah, we are so curious to listen to you, Martin, and very happy to have this opportunity. And I hope that was an okay introduction of you. So welcome to start your webinar.
Thank you very much. Good morning, everyone, and thank you for giving up your time this early morning. And thank you to the Swedish Geotechnical Society for inviting me to speak. I'm going to talk to you today about groundwater control for construction. This is based on my work of my practice, Preene Groundwater Consulting, which is now part of Richter. So the main part of my talk is about the different technologies we can use to control groundwater for construction projects, such as a tunnel or a deep basement. I'm going to begin with introduction and definitions, and then the main part of my talk is talk about the three different approaches we can take to controlling groundwater. These are exclusion, where basically we try and keep the water out. This is pumping, where we use wells and sumps to lower the groundwater level below the excavation. And also the interesting technique of fluid counterpressures, where if we have the confined space of a tunnel or a shaft, we can pressurize that to effectively create a bubble below the groundwater level. And then I've got a few concluding remarks. So a simple definition of ground control is the process of temporarily dealing with groundwater to allow excavations to be made in dry and stable conditions below natural groundwater level. It may also be known as dewatering or construction dewatering or groundwater lowering. In my talk, I'll mainly be using the term dewatering purely because it's shorter and easier to say, but I mean the wider process of groundwater control. Another really useful term that we use in our industry of geotechnical engineering is permeability. And permeability is a measure of the ease with which water flows through a soil or rock. So if water flows easily through a soil or rock, that would be high permeability. And conversely, if the water flows only poorly or slowly, that would be low permeability. Permeability is typically given the symbol K, and in SI units has units of meters per second. And also it's also known as hydraulic conductivity. Another useful term is drawdown. Drawdown is the amount of vertical lowering of the groundwater level due to pumping. So for example, if we have an initial groundwater level of 1 meter below ground level, and we lower that to 5 meters below ground level, we've lowered it by 4 meters. So we would say that we have a drawdown of 4 meters. If we just think about the permeability of soils, and also I'm speaking to you from the north of England, where many of our soils are of glacial origin, perhaps quite similar to some of the Nordic countries. And when we describe our soil from a borehole log, the description is based on the particle size distribution in large part. And it's interesting that permeability is also related to particle size distribution. So the soil description is actually quite a good high-level indicator of permeability. So if we think about a very high permeability soil, this will be thought of as water-bearing. And if we dig an excavation below the water table, we're probably going to get groundwater problems. And examples of a high permeability soil would be a coarse-grained soil, such as maybe a glaciofluvial sand or gravel that has quite a coarse particle size. At the other end of the scale, very low permeability soils we can excavate into those, and we tend not to have groundwater problems. These tend to be soils where the dominant particle size are clays or silty clays. So, for example, that might be a till deposit. There's an interesting set of soils that are what are called intermediate soils, and these are ones where either the dominant particle size are either very silty sands or silts, or maybe like you would get in a glaciolacustering deposit, you get a layered sequence of silt, sand, and clay. These soils are of intermediate permeability. It's often quite difficult to predict whether they'll behave like a water-bearing soil or like a low permeability soil. Sometimes we carry out ground control in rock. Most of you will know that in rock, groundwater flows quite differently. Typically, the dominant forms of groundwater flow in rock are through fractures or other forms of discontinuities. Though sometimes in weathered rock or in sandstone, you can get significant water flow through the body of the rock itself. This photograph on the right shows an example of some limestone exposed in excavation. My yellow site notebook is used for scale, and you see here that there are two sets of principal fractures. One set that's approximately horizontal and one set that's approximately vertical. And these intersect, you can clearly see that the groundwater flow is going to be controlled by the intersection of the fractures. So now I'm going to talk about these three different approaches to ground control that I mentioned. This is exclusion, pumping, and counter pressures. I'm going to begin with exclusion. And exclusion is very simple in concept. Basically, we are intending to install a notionally impermeable physical cutoff wall all the way around the excavation to basically separate our excavation from the wider groundwater regime and exclude the groundwater from our excavation. This is a schematic diagram of an exclusion system. Here's the excavation. You can see that the vertical dart line is a vertical cutoff wall we've installed around the excavation. And we imagine that this extends out from the excavation and continues out of the screen and forms a complete barrier around the excavation. In this case, there's a low permeability strata, maybe a glacial till or a mudstone at depth, and our vertical cutoff wall is designed to penetrate down into this low permeability stratum. So therefore, the combination of the artificial vertical wall we've created and the low permeability barrier at depth effectively creates a complete barrier around our excavation. Therefore, if we use a sump pump here to drain away the trapped water inside the soil or rock inside the excavation, we can pump quite small quantities of water to lower the groundwater level inside the excavation here. And once we've lowered we've removed the trapped water, the actual continuing pumping rate will be very small because we're only dealing with leakage through the wall. A really key point to note here is that even though we've dewatered inside the excavation, the water on the outside is hardly moved. And this is a really positive benefit of the ground control by exclusion method. It means we can dewater our excavation while hardly disturbing the water level outside. So maybe we're worried about settlement impacts, or maybe we're worried about drying out timber piles outside our excavation. That might be one driver why we would go down the groundwater exclusion approach. There are various different techniques we can use to create these the vertical barriers. And I'm going to go through a few of these in turn. One of the most common approaches are a type of displacement barriers. And with displacement barriers, we don't excavate any material. We basically drive a barrier in the ground and we displace the soil. And the most common form of creating such a barrier are the steel sheet piles, which many of you will have used. The steel sheet pile method involves taking a steel section that's set vertically underneath a crane typically, and is either driven, pushed, or vibrated into the ground. And a series of sections are installed next to each other, and they connect to each other via a clutch or an interconnection, so that this series of these individual sheet piles can form a continuous barrier. This photograph here shows a circular excavation where the ground level is up here, and we've dug down to here in a glacial sand and gravel. And these are the vertical sheet piles forming the barrier, and these hoop steel beams are the wailings which are providing structural support to the circular barrier. So in this case, the sheet pile cofferdam serves two purposes. First of all, it supports the ground as an excavation support method, but for our interest, it also acts as a barrier to groundwater flow, because here the blue pipes are the dewatering wells that have lowered the groundwater level to below the dig, but outside the groundwater level is much higher. In this case, without the barrier, we would have had to have pumped a much greater dewatering flow rate. Another form of exclusion techniques are the excavated barriers. This is where we excavate typically a narrow trench, remove the natural material and replace it with something of lower permeability, thereby creating the barrier. One approach that is used is the concrete diaphragm wall. In this case, we use special grabs or cutters to excavate a narrow trench, which is kept full of bentonite slurry. The purpose of the bentonite slurry is to support the excavation while it's being dug. Then once the excavation is completed, we then tremie into place concrete, place reinforcing bars in it, and effectively the diaphragm wall method allows us to create an in situ concrete wall. This is a picture from a project in the Middle East, and you can see here that it's a rectangular excavation, and this is the concrete diaphragm wall around the edge of the excavation. And in this case, the diaphragm wall has been used as part of the permanent works. It's been used as the wall of the deep basement. And that has the advantage with concrete diaphragm walls that they can be used for the temporary works purposes to exclude groundwater, but also can be part of the permanent works. In this case, we have the blue pipes are dewatering wells, dewatering inside the wall, and this is lines of ground anchors which have been used to support the excavation in the temporary case, because in the permanent case, the internal structure of the building will support the diaphragm wall. This is just a diagram of how diaphragm walls are constructed. Even if we're constructing a very long diaphragm wall, we don't construct it in one operation. It's normally constructed in what's known as panels, and a grab or a trench cutter would excavate one panel that will be dug, supported by bentonite, then reinforcing cages added, and concrete is placed, and we end up with a single panel, effectively reinforced concrete, sort of hidden in the ground. Then after this concrete has gained some strength, we come along and we excavate in between two neighbouring panels, and then in this way, a series of panels are used to form a complete and long diaphragm wall. It's worth noting that if you do get diaphragm walls that do have problems forming a barrier, if they do leak, it's often these joints between the panels that are the cause of the leaks. One issue with diaphragm walls is each panel is quite long. It might be several meters long. So if you're trying to create complex shapes, maybe for a circular shaft or for excavations that have corners in them, diaphragm walls are not very flexible. So increasingly, people are using secant pile walls to form groundwater barriers. This approach uses bored concrete piles that are maybe anywhere from 600 millimeters to maybe 1.5 millimeters diameter. And these are installed at a spacing of less than one pile diameter. And because they're spaced at less than one pile diameter, the adjacent piles cut into each other. And therefore, if you do this correctly and get the alignment right, this forms a continuous concrete barrier. This is a picture of the edge of a circular shaft supported by concrete secant piles. These, you see that every other pile has a steel reinforcement in it. That pile is reinforced, that pile is reinforced, and the intermediate piles are typically not reinforced. And there are different ways of making these combinations up. Still talking about excavated barriers, a related approach is the bentonite slurry wall or bentonite slurry trench. In this case, we actually do excavate the trench in one continuous operation, and we don't replace the bentonite with concrete. What we do is we either add some cement to the bentonite to make the bentonite go slightly hard, or we make a mixture of bentonite and soil, and we create a low permeability barrier in that way. This diagram shows how a long reach back actor excavator would excavate and work, in this case, work in this direction. And the way to visualize these walls is that if we add some cement to the bentonite and we mix it thoroughly and it solidifies, the consistency of the solidified cement bentonite wall is probably like hard clay, again, maybe like a glacial till. So it's quite a strong wall, but it's probably not sufficient to act as a structural barrier, say, for the permanent works. This diagram, this picture shows a large excavator for slurry walls. This is a very large machine. This is a 125-ton machine capable of digging down to about 25 meters depth. But again, if you're digging in glacial soils, cobbles and boulders can be a problem. And sometimes the deep trenches are excavated by clamshell grabs or hydro mills, like you might use for a concrete diaphragm wall. And now I'm going to move on to injected barriers. And injected barriers typically are the grouting techniques. This is a very old technique that was first developed in the 1850s. And it's very simple in concept, a little bit more complex in practice, and basically involves getting a liquid that you have at surface, drilling some boreholes and injecting this liquid, known as a grout, into the ground. And the concept is the liquid flows into the pores of a soil or the fractures of a rock, and then ideally it solidifies and hardens in the soil pores of the rock fractures, thereby blocking the pathways for groundwater flow. So you end up with a situation where you have effectively created a zone where you have the grout within the soil, within the rock, This is so-called treated ground that is of lower permeability than the natural material, and therefore you can form this exclusion barrier. The most common form of grouting is using cement-based grouts, where you literally get a mixture of cement and water to form suspension. This is injected into the ground. You can also get more expensive versions of cement where the cement is ground down finer and the cement particle size is much smaller. These are known as microfine or ultrafine cements, and these can also be used in lower permeability soils and rocks. The real challenge with grouting is that the grout really doesn't travel very far into the soil or rock, so you need to have very closely spaced boreholes. The reason for this is that with cement grouts, the particle size are actually quite, the particle size of the cement are actually quite large in comparison to the pore size or the fracture size in the rock. This is a sort of a cartoon-like diagram produced by one of the grout manufacturers, but it just shows how that we think about the cement particles being quite large in comparison to soil pores or rock fractures. And if you try and inject these grouts into fine-grained soils or rocks with narrow fractures, these large particles just block, and that's why you don't get the grout penetration very far into the rock. There are more specialist grouts, some of which are true solutions, and some of which use colloidal silica, which are these particles here, which are around about 1/1000th the size of a cement particle. But these specialist grouts are much more expensive and much more specialized to use, but can provide effective results. So the grouting techniques I've just described have been so-called permeation grouting or rock grouting, and the essence of those methods is that we're trying not to disturb the ground. We're literally trying to gently push grout fluid into the ground without disturbing the ground. But there's another approach known as jet grouting, where we deliberately try and disturb the ground. This approach involves taking a drilling rig and drilling the drill stem down into the ground, and the bottom of the drill stem has a special jetting pipe on it, which has horizontal jets coming out of it. Once the drill pipe is down to full depth, these jets are turned on, and the horizontal jets of a combination of grout, air, and water jet out horizontally. And the concept is that this pipe is rotated and then raised, and the jetting action of the jetting head washes the fine particles out of the soil to the surface. And as we raise the jetting pipe, we create an approximately cylindrical column of disturbed ground into which we've placed this grout. So you end up with this irregular column of the coarser part of the soil or weak rock, plus the injected cement grout. And effectively, you can visualize it, I think, as creating an in situ concrete from the injected grout and the coarse particles of the soil. And one of the very early trade names of jet grouting was actually soilcrete. And I think they were trying to say that what we're doing is we're creating these in situ concrete columns. This top picture is a diagram of a jet grouting rig where, just for demonstration purposes, they're running the jetting head above ground level. So you can see here the very powerful horizontal jets that cut a circular column. And this diagram here just shows there are various combinations of jetting heads, some of which have a single jet grout, some of which have a jet that's a combination of grout and compressed air, and some have a water and air jet and a grout jet. But it just shows how the different methods, and these affect the column diameter you can cut and how deep you can treat as well. So I'm going to go on to perhaps the most interesting of the exclusion methods, and this is artificial ground freezing. And this is where we use a refrigerant to deliberately freeze the ground. And the thing about frozen ground, which of course is the water frozen around the soil or rock particles, it's very high strength and it's a very low permeability. So as well as forming a groundwater barrier, it can be very effective at supporting, say, a tunnel or an excavation. The ground freezing method begins by drilling a series of freeze holes, typically maybe around about 1 meter centers. These are drilled like a piezometer, but we put a piezometer pipe in them that has no slots in it, because we're going to circulate refrigerant down these holes, and we don't want the refrigerant to go into the ground. So this would be a piezometer pipe, as it were, with no slots in it. We then circulate our low temperature refrigerant down each hole in the line, and then this is going to freeze the ground locally around each hole, and we get what's known as an ice cylinder builds up around the hole. As we keep on circulating refrigerant over days and weeks, the ice cylinders around each hole grow in diameter, and they will eventually meet and coalesce, and we get what's known as closure. We get the completion of a continuous freeze wall. This is what it looks like in practice. So here, a mine shaft is being sunk. This is where the shaft is going to be. And a series of vertical freeze holes have been installed around the outside. And we have refrigerant being recirculated around these pipes. Everything is very heavily insulated because, of course, we want to not waste energy, but we want all the coldness to go into the ground. This white colour here is actually ice frozen on these insulated pipes. And that's just where the moisture in the air touches the pipe and freezes. There are two different types of ground freezing method. The most commonly used and the most economical is the so-called brine freezing method. And this is perhaps quite easy to understand because we all have a refrigerator in our kitchen back at our homes or our apartments. And basically, in this case, we build a very large refrigerator that chills calcium chloride brine down to between -35 and -40 degrees Celsius. And we circulate this low temperature refrigerant around these freeze holes. And then this refrigerant chills the ground. It comes out of the ground a little bit warmer than it went in, and then we recirculate it back to the refrigerator and we chill it again. And this method is quite widely used, but it is perhaps rather slow, and sometimes it can take several weeks to chill the ground sufficiently to get a complete freeze. Sometimes when there's more challenging ground conditions, or if there's an emergency, you need a rapid freeze, a more extreme form of ground freezing can be done, which is the liquid nitrogen ground freezing. This is a little bit more sort of weird as a method, because you literally get a tank of liquid nitrogen on site, which has a freezing point of around about -180 degrees Celsius, and you pipe the liquid nitrogen directly down these freeze holes, and you circulate it through the system, and then you bring it to the surface where it's vented to atmosphere. If you get the design right, you want the nitrogen changing from its liquid state to its vapor state within the freeze holes. Because if you go back to your basic physics and chemistry, when the nitrogen changes its state, it will absorb the latent heat of vaporization, which means that it absorbs an awful lot of energy for not much temperature rise. As I said, liquid nitrogen ground freezing is more expensive, but it's quicker, and sometimes you can achieve a freeze within 1 to 2 weeks of turning on the refrigerant. So I just want to finish talking about exclusion methods by making a point that I'll come back to later on, is that these different techniques, they are not always interchangeable. Some of them will work only in a certain set of ground conditions. Some of them only work in certain depths. So when you are planning a ground control system by whatever method, including exclusion, you must understand the system and select an appropriate method. So here, for example, you can see that cement-based grouts only work for this permeability range from maybe 10 to -4 meters per second up to 10 to -1. Chemical and resin grouts work a little bit lower, but even they have a lower permeability limit. You can see here that physical cutoffs, putting a physical barrier in the ground, does tend to work across all permeabilities. But for example, if you have very hard rock, it can be difficult to drive a barrier. If you have big cobbles or bolts in glacial deposits, that can cause problems. So a really key point is to understand the application and limitation of the different methods. So now I'm going to move on to the next group of techniques. These are ground control by pumping, and these are perhaps the easiest to understand. This is what we call dewatering, where we pump from a series of wells or sumps and we lower the groundwater level. If you look at this diagram here, we have a series of, in this case, 6 widely spaced deep wells around the excavation. We pump from each well. And if you've studied any hydrogeology, you know that when you pump from a single well, you lower the groundwater level and you get what known as a cone of drawdown centered on that well. Whereas if you have a series of wells that pump simultaneously, the cone of drawdowns between these wells will interact and will add and combine. And eventually you can get this cumulative drawdown effect where each of these individual wells creates a large amount of drawdown, which means that we can achieve the water level to be lowered below our excavation. We then carry out this excavation in dry and stable conditions. And that is essentially the principle of ground control by pumping. Before I go on and talk about groundwater, though, I want to talk briefly about surface water. You know, wherever you're listening to this from, it's going to rain on your site. And if you dig an excavation, if you don't control the surface water, that rainwater will end up in your excavation and it will cause you problems. This is a photograph from a project in the Republic of Ireland, dug in some deep glacial deposits. And for scale, this excavator is a large 45-ton excavator, and that is the 6-wheel drive Volvo dump truck. And so if you look at the wheels of the Volvo dump truck, that wheel is maybe 2 meters diameter, and you see the water is halfway up the wheel. So there's around about 1 meter of water in the excavation. That isn't groundwater, that's mainly surface water that's come from the surrounding area during the heavy rains. You can see that this is just not an efficient way or a safe way to run an excavation. It's going to slow down the excavation, it's going to degrade the spoil, it's going to cause problems. Here's the same excavation a couple of weeks later when we'd done some very simple things. We created a cut-off drain at ground level around the excavation, which means that water falling on the surrounding ground was intercepted and did not find its way into the excavation. We put some sump pumps in here to control the water, and we laid some coarse stone to allow the dump trucks to move more freely. And you can see that this picture is much more efficient. It's going to be saving them many hundreds of thousands of euros over the life of the project because it's going to speed up the whole process. But it is interesting that surface water control is often not carried out very effectively on many projects. In terms of surface water control, it's all very simple, really. You need to control the source of the surface water to prevent water from the surrounding ground going into your excavation. Don't generate surface water yourself. Sometimes you see people washing down trucks or washing down concrete in excavations. That can be done elsewhere to avoid pollution problems. Inside the excavation, you need to collect the water. So normally there would be a series of drains or sumps, and then you would pump the water away from these areas to keep the water to keep the excavation dry. A really key point is you probably need water treatment, because surface water, if you go back to that last picture, the water looked very dirty, and that's because the water has been sitting on the exposed soil or rock. It will pick up fine particles. You cannot discharge dirty water to the environment. It will cause problems. So normally you'd have to do some sort of water treatment. You have solids removal like settlement tanks, or in the UK we have lots of specialist treatment systems by silt busters and other companies where they use lamella settlement tanks to try and remove the silt from the water. But surface water control is absolutely part of ground control and must be considered. So I'm now going to talk about different forms of ground control, and it's worth just pausing for a moment and thinking about two different types of ground control. The simplest method is what's known as open pumping, and this is where we effectively pump the water from within the excavation. And I'll talk about sump pumping in a moment. And this has obvious practical advantages. It's very simple and it's going to be cheap, but it has other disadvantages too. First of all, you cannot lower the groundwater level in advance of your excavation. So this means that you're always going to have some form of wet condition in the bottom of your excavation. And also, you tend to be drawing groundwater towards your excavation. And so if you're in a soil that maybe it is at risk of being unstable or erosion and so on, you're getting this concentration of flow where the water enters the excavation, and this can cause problems. The alternative, and in my view, better approach to ground control is what comes pre-drainage. And this is where we use wells that are typically outside the excavation, though they can be inside. And the idea is we lower the groundwater level in advance of the excavation. And this can give you a totally dry excavation and a totally stable excavation, and has many other advantages. And sometimes I think people don't appreciate the difference between the two approaches. So I'm going to take you through the four main approaches of ground control by pumping. First of which is sump pumping, which is this open pumping approach I mentioned. Then we have three pre-drainage methods, which are well points, deep wells, and ejector wells. And these are basically listed in order of sophistication. So I'm going to start with the simplest method and then go on to the increasingly more complex methods. But before I do that as well, I just want to put this diagram up. So this diagram is from a UK document called Survey Report C750, Groundwater Control Design and Practice, of which I was one of the co-authors. This is probably the UK's sort of de facto guidance on groundwater control. And this diagram is a really useful diagram because it shows the range of application of the different techniques. And if we look at the vertical axis here, this is drawdown, which, as I said, is the amount of lowering of the groundwater level. So we have 5 meters, 10 meters, 15 meters, 20 meters. Along the horizontal scale, which is the log scale, we have permeability. So down here is 10 to the minus 8, 10 to the minus 7 meters per second, which would be low permeability silts maybe. At the very high end, we have 10 to the minus 2, 10 to the minus 1 meter per second, which is a very open gravel. And in the middle, we have 10 to the minus 5, 10 to the minus 4 meters per second, which say would be a sand of some description. And you can see that there are areas where different techniques are indicators being applicable. And also you can see that the lines between the areas are blurred, and that's to show that there is not a sharp, precise division between the different methods. Now I'll illustrate how you can use this. So let's say we're going to sink a shaft and we need to lower the water table by 15 meters. So we come down and we come down to the 15-meter line. And let's say we have estimated that permeability is 10 to the minus 4 meters per second. So our point now is here. You see, this is well within the deep well zone. And that would mean that as a designer, I would be thinking that in all probability, the deep well method, if we're going down the pumping route, is the most appropriate method. This does not replace the overall design process. It does not mean we don't have to do more detailed work, but it's the starting point to direct the design. Equally, if I'm reviewing a design, which I often do, and if someone says to me that they've got an ejector well system for a 15-meter shaft with 10 to the minus 4 meters per second, I'm going to check that very carefully, because either they've got an inappropriate design, or maybe they're misreporting the permeability. So it is a very useful tool for design checking and for high-level design. The other thing is, it lets us think about risk. So maybe the permeability of the soil isn't 10 to the minus 4, maybe it's something like 3 times 10 to the minus 5, or 4 times 10 to the minus 5, which would be there. That's still within the deep well zone, but it's getting close to the border with ejector wells. And if ejector wells and deep wells tend to work differently in different conditions. So if that is where our point of permit is, I maybe want to do some further investigation and decide whether I really think the permit is that value, to make sure that I don't choose the wrong dewatering method. So now we'll go through the different methods. And as I said, sump pumping is the simplest method. It's very simple to understand. We have an excavation and we create a deeper part of excavation, which we call the sump. And ideally, we dig some drains and we direct the water that enters the excavation to flow to the sump. We have a simple, robust sump pump, either a submersible pump or a suction pump, and we pump the water away. This is a schematic diagram, and this is a real case here. You see here we have the pump, a deep excavation, the sump has been dug, and the water is flowing towards us. The first thing you can see is this isn't giving us great excavation conditions, that if we wanted to maybe construct high quality concrete in this excavation, it's going to be difficult with the water sitting in the excavation. In this could actually be improved, that maybe if they dug a narrow trench down here to direct this water more directly to the sump, that would make this better, but it's still not going to give perfect conditions. So if we needed better working conditions in the excavation, maybe we could have thought about switching to a pre-drainage method that can give you better results. In terms of the characteristics of sump pumping, because it's an open pumping method, it can only lower the groundwater level to the base of the excavation. We can't lower the groundwater level in advance of the excavation. The sumps take up space within the excavation, and it's limited to use in relatively coarse soils and stable rocks, because if the material is susceptible to groundwater-induced instability, the flow of groundwater towards the excavation can cause instability. And just like surface water, when you pump water from a groundwater sump, the water has flowed across the soil or rock. It will have picked up particles, it will be dirty, and it may need to be treated before you discharge it. So now if we move up to the next level of sophistication, I'm going to talk about wellpoint systems. And these are the first of the pre-drainage methods. And the idea of a wellpoint system is we install a series of closely spaced shallow wells known as wellpoints to form a curtain or a barrier around the excavation. This is one wellpoint here. There's another one there, and you see all the way around they form a continuous barrier. And the idea is that we're trying to intercept the groundwater before it actually enters the excavation. The way that the wellpoint system works is we have a pump here that creates a partial vacuum, a pressure below atmospheric pressure, and that partial vacuum is transmitted around the excavation in this header pipe that's normally about 150 millimeters diameter. Every 2 meters or so, we have a well point that's connected to the header pipe by a flexible connection of valve. So basically the partial vacuum starts in the pump, it comes round or along the header pipe down into the well point. The well point has a perforated filter on it, and so the partial vacuum here draws the groundwater in, lifts the groundwater up, and the water from all the well points is collected together and discharged away. And effectively, the header pipe acts as a manifold, which means that just one pump can pump on anywhere from 50 to 100 well points at any one time. So it can be a very effective and efficient way of pumping. This is what it looks like in practice. Here we have a small excavation, and you can see the green pipe is the header pipe being laid around the excavation, and every 2 meters or so there is a well point with this flexible connection to the pipe. The pump is over here. The pump looks like a box because it's silenced, because a key thing with most pumping systems is they pump 24 hours a day, 7 days a week. So you need to keep the noise down, particularly when you're working in urban areas. This is a silenced diesel pump. It's still quite noisy, even with all the enclosures. And if you do need to keep the noise really down, you need to go for electrical pumps, which are much quieter. This excavation isn't at full depth here. They've just dug down to place the first support frame, but here they've dewatered it inside some trench sheets, and they would excavate later. A really key limitation of this method is that because it relies on the suction lift principle, the drawdown you can achieve with a single stage of well points is limited to about 4 to 6 meters below the pump. So the most common application of well points is for fairly shallow excavations, maybe for shallow basements or for pipelines. If you need to use well points for deeper excavations, you can use what's known as a multi-stage well point system. This is a picture here, and it's quite complex, so I'll explain what's going on. What's happening here is that this pump here and this line of well point, which goes around here, is the first stage of well points, and they've been used and installed, and they've lowered the ground level by about 5 meters in this sand. But we need to go deeper. So when the excavation's been dewatered 5 meters depth and dug down to that level, there's a pause, and a second stage, stage 2 well points was installed with a separate pump, and then that was pumped and excavated, and then that's still not deep enough. So then a third stage of well points was installed. That was pumped and dug, still not deep enough. And then in this case, a fourth stage of well points was installed. And one point to note is that each stage of well point achieves less and less drawdown because it's working harder and harder. And you see here that that's a lot of equipment, a lot of space being used to get down to this depth. And nowadays, people tend not to use multi-stage well point systems. They would tend to use something like deep wells, which I'll talk about in a moment, which can achieve the drawdown to full depth in one operation. So I just want to talk briefly about how we install well points. Many of you will have worked on jobs where you've installed monitoring wells or piezometers using a drilling rig, where you put in a 50mm diameter pipe to 6 meters depth or so. Well, that's quite a similar design, as it were, to a well point. A well point pipe is typically a plastic pipe anywhere from 38mm diameter to 50mm diameter. It's installed to 6 meters depth with a filter on the bottom. And we could drill them in with drilling rigs, but we have to put a large number of these well points in the ground. Even a small excavation with well points at 2 meter centers might have 50 or 100 well points around it. And it will be too slow and too expensive to drill these in with a drilling rig. So we developed the method of jetting. This involves a water supply that goes to a high pressure jetting pump. The jetting pump is connected to a steel tube known as a placing tube supported by an excavator. The top of the tube has a cap on it, so that when we pump high pressure water into this jetting tube, the only place the water can come out of is the bottom of the tube. The excavator then lowers this placing tube into the ground, and the combination of the weight of the tube and the aggressive jetting action of the water will, in favourable conditions, wash this tube quickly into the ground. And so if you're in a fine sand, like we saw in the last picture, a 6 meter long jetting tube will wash into the ground in round about 30 seconds to 1 minute, very, very quickly, much quicker than you can drill. What happens is that once this placing tube has been washed into the ground, you turn the water off, you take the cap off the top, you install the plastic well point in the inside the placing tube, and then you withdraw the placing tube while placing filter sand around the outside the tube, and then you track the excavator 2 meters down the line, and you repeat the process again and again. And a good crew can install maybe 50 well points to 6 meters depth in favourable conditions in just one morning, and that's much quicker than you can drill piezometers, for example. Of course, this method has its limitations, like all things, and if you have cobbles or boulders present, or if you're in clay layers, the process can be much slower. I'm now going to move on to the deep well method. And the deep well method is quite easy to understand in that we install a well like you would have for a water supply well, for a house or for a community, and we install a slimline borehole submersible pump of the sort made by, for example, by Grundfos. And each well we have, the well's been drilled by a drilling rig. It has a perforated plastic liner in it. The submersible pump, we provide a power supply for a generator and control cabin, and the well pumps and creates this cone drawdown. And then we have a series of wells. There are 6 wells around this particular excavation. Together, they lower the groundwater level, we get the cumulative effect, and we can dewater this excavation. And this is very effective for deeper excavations. And I've worked on jobs where I've been sinking shafts 50 or 60 meters deep, and we've installed a single stage of well points, and they've been able to cause very significant lowering. And in the mining industry, for example, wells like this are sometimes used for excavations that are hundreds of meters deep. This is a picture of an excavation in glacial soils in Canada. And here we can see that we have a series of wells, one here, and a line going away. These are about 20 meter centers. And you can see some factors here. This is the well. This is the pipe feeding the water away, and it's quite a high capacity system. So here, the water from each well is pumped to a water collection main, which carries the water away. And here you can see the power cables, because each well is fed from a generator in this case. This is an example of a smaller scale wellpoint system, deep well system, sorry. Here's the top of the well. The pump is out of sight. The well is kept to the surface by a rising main. There's a flow meter, control valve, and control system there. So it's actually very simple and easy to understand. The drawdown is limited only by the depth of the well and by the soil stratification. Typically, wells are installed at quite wide spacings, maybe a spacing of between 10 meters and 60 meters between wells, which is much wider than well points, like we discussed. And also, it may be prone to clogging. These wells may be prone to clogging due to groundwater chemistry effects, particularly if there are high levels of dissolved iron, Fe, in the groundwater. You get these brown ochre deposits, and these can clog the wells. But you can deal with that. It's just a maintenance issue. So I'm going to talk very briefly about the ejector well system. This is a specialist technique that uses a nozzle venturi system to create a vacuum in a sealed well. What actually happens is you have a reservoir of water at ground level, and you put that through a high pressure supply pump, and you circulate high pressure water, and you actually inject high pressure water down into the well. And this seems quite a strange thing to do, but in the bottom of the well, there's a nozzle and venturi arrangement, which has a non-return system in it, which hopefully makes sure that the injected water does not go into the ground, and the injected water is forced to return back up the pipe through a separate system, and then it's recirculated continuously. But by passing the water through the nozzle venturi, it goes through this nozzle at a very high velocity. And if you go back to basic fluid dynamics, this high velocity creates a low pressure, so you get a very high vacuum right here in the bottom of the well. And I've used these very effectively in soils of low and intermediate permeability, for example, in glacial lacustrine deposits that are very silty or very laminated. Deep wells and well points can sometimes not be very effective, but ejector wells can be very effective because they create this high vacuum. So now I'm going to talk about the third and final type of methods, and this is maybe slightly more conceptually more strange, I suppose. And it's the idea that we are going to use a fluid counterpressure to keep the groundwater out. And this is based on the concept that if we have a confined space, such as a tunnel or maybe a shaft, we can pressurize this confined space. And if we raise the pressure in here with a fluid, we can balance the groundwater pressure and effectively keep the groundwater out. There are two main methods that's worth talking about. I'm going to talk about compressed air tunneling and closed face tunnel boring machines. So I'm going to talk about compressed air tunneling, and this is a very old method. It was developed in the mid-19th century. For example, the Brunel family, Mark Brunel and Isenberg Kingdom Brunel, used it on some of their works under the River Thames. And the idea is we have a tunnel here that we're constructing below ground level. And also the tunnel has its primary lining, its segmental lining, and we have a tunnel shield. Now, if we create a pressure bulkhead and an airlock inside the tunnel itself, and we pump in compressed air from a compressor, we can, if we put enough air in, we can pressurize this zone between the tunnel face and the airlock, and we can raise the pressure in the tunnel to approximately match the ground pressure. And if we do that, we can essentially keep the groundwater out. It's not that simple because you can't precisely match the groundwater pressure with the air pressure. Because this triangular diagram here will be what you're familiar with. This is the groundwater pressure, and this means the groundwater pressure increases by 10 kilopascals for every meter depth below the water table. Whereas the air pressure in the tunnel, because the air has a very low density, the air pressure in the tunnel basically is constant between the tunnel in crown and the tunnel invert. So you can see that you can't get a perfect match between the air pressure in the tunnel and the ground pressure. So what you tend to do is you have to balance the water pressure by setting the air pressure in the tunnel around about the midpoint of the tunnel. This means that at the top of the tunnel, the air pressure is greater than the water pressure, and you get some air loss. And at the tunnel invert, the air pressure is less than the water pressure, so some water will come in. But you can get essentially a relatively dry working environment. And then when you have this, the way the tunnel is constructed is that your workers, your operatives, enter the compressed air zone through an airlock, and then they work in an atmosphere above atmospheric pressure in a compressed air environment, like deep sea divers do. And just like deep sea divers, they're at risk of various health problems. If they don't decompress properly when they leave the compressed air environment through the airlock, they're at risk of what's known as the bends, or decompression sickness, where they can have brain problems due to nitrogen bubbles forming in their blood. But it also can get what's known as bone necrosis or bone rot, where the nitrogen bubbles cause erosion of their bones. And I've worked with miners who worked in compressed air who had to have hip replacements at very young ages because of these health problems. So up to about the sort of 1980s, compressed air tunneling was used very widely. But since then, the health risks have been very much recognised. And now compressed air tunneling tends to only be used in very specialised circumstances under close medical control. For example, where operatives need to enter the front of a tunnel boring machine to replace parts for short periods of time. So since sort of the later part of the last century, the main fluid counterpressure method has been so-called close-face tunnel boring machines. And this is where you have the tunnel being driven and you have the shield, and then we construct a pressure bulkhead, a strong pressure bulkhead in the front of the shield. And this means we can cause a fluid to be created in front of the pressure bulkhead behind the rotating cutting head, and we can manipulate the pressure of this fluid to support the ground and keep the groundwater out. And this means then that our workers in the tunnel can work effectively in atmospheric pressure, and broadly speaking, in almost like a factory-like environment. You can be there working in your t-shirt many meters below the groundwater level because you're working behind the pressure bulkhead, but you're relying on this fluid counterpressure approach. There are two types of fluid counterpressure. There's the EPB, or earth pressure balance machine, and there's a slurry machine. The earth pressure balance machine effectively uses the fluid pressures from a paste that's formed from the cuttings, the soil or rock eroded by the cutting head, a paste formed from the cuttings, groundwater, and some conditioning agents, such as polymers or foams are added. And the idea is we control this fluid in here, and there's what's known as a screw conveyor, and this screw conveyor is used to manipulate the pressure of this fluid to keep the groundwater out and to support the face. And companies like Robbins and Heron Connect make these machines, which cost many millions of euro. Then the other approach is a slurry TBM, and this uses a bentonite slurry typically to support the face. It's almost similar to the diaphragm wall method I described, where we have the trench full of slurry to keep it stable. And the way the slurry method works is at ground level, we have a slurry plant, and we create a large volume of bentonite slurry. This is pumped to the tunnel face, and this space in front of the pressure bulkhead is filled with bentonite slurry. We're able to control the pressure of this slurry, and then this supports the face. As the rotating cutting head cuts the soil and rock, these cuttings are entrained in the slurry, and so then the slurry containing the soil cuttings is pumped back to the surface. There's a slurry treatment plant which removes the cuttings, and in a continuous process, the slurry is pumped back to the face in this way. And most modern tunnels in difficult ground conditions are constructed by one type or other of this closed-face tunnel boring machine. So to summarize, I've taken you through the three different approaches to ground control: exclusion, where we're trying to keep the water out; pumping, where we use wells and sumps to lower the groundwater level; and fluid counterpressures, where we have a confined space like a tunnel or a shaft, we can pressurize that to keep the water out. And I've described the various different technologies which can be used to apply each approach. The really key thing, the key message from my talk are that these techniques are often not easily interchangeable, and they often only work in a narrow range of permeability and for certain depth ranges. So it's really important that engineers, geologists, designers, and analysts, they understand the capabilities and limitations of these different systems. It's not sufficient for us to understand the ground conditions. We need to understand both the construction project, what does the construction project want in terms of ground control, but we really must understand the technologies. You don't need to understand it on a nuts and bolts level, like perhaps I have learned to do over 30 odd years, but you can understand the limitations so that you can get the right advice, you can get the right contractors on board. Because if you have to change dewatering technology or approach partway through the project, it can be a very painful and slow process. And there's a real risk if you don't understand technology, you're going to misapply it, and it's going to lead to problems and delays. Well, that's the end of my talk. I hope you've enjoyed your morning with me, and thank you for your time.
Thank you very much, Martin. We have had quite many listeners, more than 110 attendees, actually, and we have some questions here. Maybe start with a question from David or David. Is there any sort of best practice regarding the distance between well points? For example, one well point per 2 meters seems quite expensive, but is there any common distance to use?
I think there's no best practice, but there's a lot of experience. And in very high permeability soils, such as a very coarse gravel, you need lots of well points at close spacings to get the pumping capacity, because each well point will only pump about 1 litre per second. There's like a hydraulic limit on it. So I have worked on projects where people have installed them at 0.5 metre spacings, but that's very extreme, and that was for a specific reason. The vast majority of well point systems are at a spacing of between 1.5 and 3 metres. It's very unusual to have them beyond that spacing. And my interpretation is the well point method is over 100 years old, or well, around about 100 years old. And it's been developed really not theoretically, it's been developed by experience. And I think so if you find a design where you're outside that range of maybe 1 metre to 3 metres, and you think your design is saying you need to have a different range, then I think it's the wrong method. That's one of the indicators that maybe, like I said, that you're looking at a problem where you need to look at a different method. Like a very wide spacing of well points means the flow rate might be very low, and so maybe you can sump pump it. And a very close set of well points means maybe the flow rate's very high, maybe for deep wells or something similar. So that's not a great answer, because I don't think there is a simple answer to that. But the vast majority of well point systems are in this range, probably 1 metre to 3 metres.
Thank you. I think it was a good answer. Maybe this question then, could one make a cost comparison between using deep wells for drawdown compared to exclusion methods? What are the cost differences? Could we earn money on pumping instead of exclude, or is it the opposite? Or do we need both?
Well, I think that's a really difficult question. Over the years, I've written books and guidance, and we always have a section on cost, and we've never been able to come up with a way of being able to compare different methods. Because sometimes if you read a book on ground treatment, sometimes you can find it would say that there is so many euros per cubic meter of treated ground, or maybe for diaphragm wall, it'd be so many euros per square meter of wall. Because dewatering systems are so difficult, there's no generic comparison. You would have to look at your project and cost it then. And it's even more difficult when you are comparing a pumping system with an exclusion system, because maybe if you're being very efficient, you could use your exclusion system, your walls, to be part of the structure. And so a diaphragm wall, for example, is very expensive. And to put in a diaphragm wall is almost certainly going to be more than a temporary works pumping system. But if the diaphragm wall is being part of your structure, that can be a very cost-effective way, because you are using it twice. You're having it as a temporary barrier and your permanent barrier. And the only way you can compare that is to look at your own project. And the other thing is, an exclusion method might have many benefits with risk, because let's say you are in the middle of a city in Sweden where there are many buildings on timber piles. An exclusion method could potentially reduce the risk of you damaging the neighbour timber piles, whereas a dewatering method might be much cheaper but would have risks with it. So again, not a great answer, I'm afraid, but that is one of the challenges of this field, is that there are so many different factors that generic guide is quite difficult.
Yeah, true. And then let's see here. Yeah, maybe we are now touching this question. What does the environmental code in UK say about dewatering? Do you need to apply for permits? For example, in Sweden, we work a lot with what the code, the environmental law says.
Well, the starting point is, you say, what is it in the UK? Well, the UK is 4 different countries. It is England,
Yeah.
Scotland, Wales, and Northern Ireland, each of which has its own different code and different regulator even. So that's the first point. But to pick the example of England, where we have a regulatory body known as the Environment Agency, and there is a minimum limit that if you're above so many cubic meters per day, you need to apply for what we call an abstraction license. And this is on the whole not a simple or a quick process. And part of my work is making sure clients are aware of this at an early stage, because probably some background that historically, in the past, there's not been a requirement to get a license for dewatering. It's only really been a formal requirement for the last 3.5 years. So many clients, they don't do a dewatering job every year. So often we have clients who have done dewatering before when it didn't need a license, and so now we're dealing with them, and it's the first time they need a license. So sometimes is yes, there is regulations, as we would say, and then of course the key thing, everything has to be risk based. So if you are doing a small dewatering job on a new development with no nearby buildings, the risk is low. But again, if you're doing something in a city centre or maybe near a contaminated site where you'd be worried about moving your pumping, causing the canal to move, it's obviously more risky. So everything has to be risk-based in my view. And on the whole, the regulation in the UK do sort of follow that approach.
Mm. Let's see what
I can take one here, which are quite interesting, about the freezing methods. From my perspective, it's not commonly used here in Sweden. From what I know, it's very expensive. But what would you say about the usage in Great Britain? Is it commonly used, or
no? In the UK, so it's very rare. Probably on average less than 1 project per year. Let's say in continental Europe, I get the feeling in France and Italy it's used a little bit more. It's been used on a number of metro stations and so on. And you're quite right, it's expensive, and also there isn't much expertise in it. So as it were, there's no competition in it. So if you do decide you're going to use it, you might end up paying a high price for it anyway. But I've used it on, let's say, emergency jobs, projects where there's been a tunnel collapse. And in the UK, it tends to be that because it can deal with very disturbed ground. And in my experience, when you get disturbed ground from a collapse, it becomes quite permeable and it can be difficult to dewater disturbed ground, whereas ground freezing can be really effective in those conditions. And also, particularly now, increasingly, when people are building new metro systems or new road systems, they need to at some point connect into other tunnels, existing tunnels, and it can be quite awkward to do ground treatment or dewatering where you're connecting your new tunnel to an old tunnel or an old shaft. And I get the feeling that ground freezing is often used for small pieces of work where you're connecting in. So yeah, it's a method that's used rarely. Like all the things, a term I use is I've view these methods as a toolkit. If we're trying to control groundwater, we start with a toolkit of methods, which includes the exclusion methods, the pumping methods, and the counter pressure methods. And the challenge for designers and contractors is to make the best use of that toolkit. And cost is a factor, time is a factor, and risk is a factor. And I think ground freezing probably comes along where when you are in a very risky scenario and it needs to work and you can't pump. Then ground freezing might be expensive, but it can be the best solution considering all these factors.
Okay, thanks. I think time is running out. I would like to perhaps finish with one last question. Do you have any good advice in general? Where in projects do you end up in problems? Is it like in the design, you choose the wrong methods, and that's obviously linked to your conceptual models? What's your general general recommendations from your great experience?
Unfortunately, you know, because I've been around so long, I tend to see and remember lots of problems. So I've seen lots of problems at all stages. But the big problems occur when people don't think conceptually, and when they don't try and figure out what that, because ultimately we're in construction, you know, the people who pay the bills don't care about groundwater, they don't care about the ground, they want a tunnel, they want a building, they want some, and they're trying to serve society. We're all here to serve society in some form or another. And we as geotechnical people need to communicate with them that they need to consider the risks. And that starts at planning stage, because without even drilling a single borehole, in countries like the UK and Sweden and the other Nordic countries, we have geological mapping. So the right person spending one afternoon on a computer can probably learn a lot about the potential risks for a new project, be it a house or be it a multi-million-pound project. And then we need to communicate the value of investigation to find out specific things about our site, and then communicate the value of planning to mitigate risk. And sometimes I think in projects, the geotechnical community, our voices are not loud enough, and or not early enough. So it's about a broader geotechnical point, because when you're on site, I say that when you're stood in the bottom of a 50-meter deep hole in the ground, you become very humble. You suddenly have a tremendous interest in ground support. You suddenly have a tremendous interest in dewatering, because it means something to you. The problem is when you're at planning stage, these things don't mean so much to people. And if we can communicate that, then we're helping everybody.
Yeah. Okay, it's good to hear that the challenges for our community seems to be universal. I would say that's the experience we had in Sweden as well. So yeah. Just a huge thank you, Martin, for taking your time and sharing your vast experience and knowledge on this subject.
Thank you very much.
Thank you. Bye.